Alright, hello everybody, this is Mr. Arocena, and today I'm going to be talking about magnetic fields. Alright, so let's get started. Now, some basic things about magnets. I'm pretty certain everyone's probably played with magnets of some variety in their childhood. If you didn't, kind of feel bad for you, because magnets are really fun. Anyways, so all magnets are composed of at least two poles. You have a north pole and a south pole. So similar to how electric charges have a positive charge and a negative charge. Now with magnets, they also exhibit a property similar to electrostatic charges, where like poles repel and unlike poles attract. If you remember from our electrostatics unit, we had like charges repel. Like charges repel, and similar or different, sorry, not similar, different attracts. There we go. Okay. Now, unlike electric charges, neutral objects generally don't get attracted to magnets. But there are some special cases where magnetic materials, so non-magnetized magnetic materials, will get attracted to magnets. And we'll talk about that a little later today. Alright, now what causes this attraction to magnets, or what causes this repulsion from magnets? This is the magnetic field. So similar to how electric fields create an attractive or repulsive force between charges, magnetic fields do that for magnets. Okay. So these magnetic fields are vectors, so very similar to electric fields. They have the symbol B, little arrow on top, and magnetic fields are measured in a unit called a Tesla. Measured in Teslas. Okay. All right. Now the direction of the magnetic field is the direction of a north pole and how it would move in a magnetic field based on the rules we discussed previously. And this is kind of very similar to how we arbitrarily choose a positive charge to determine the direction of the electric field. With a magnetic field, we choose how a north pole would move. Okay. So if you put a north pole in a magnetic field and it moves to the left, the direction of the magnetic field is towards the left. If it moves to the right, direction is towards the right, and so on. Okay, now one thing that magnetic fields cannot do is they cannot cross each other. So it's very similar to how electric fields don't cross each other, and you can actually use this to help us explain some of the things that magnets, some of the behavior that magnets exhibit. Right? So here are some common arrangements of magnets, and I'll draw the magnetic fields to show you what it looks like. Okay, so here's two similar poles, two north poles attracted to each other. So their magnetic fields, if I put a north pole here, according to our rules for magnetic fields, a north pole would move away from them. They repel each other. Okay, but then if they encounter each other like this, they'll also want to repel away. They could curve backwards, but then you've got more magnetic field also going that way, so those will continuously repel each other. And the same kind of thing will appear on the bottom like this. Okay, now the more magnetic field lines we have, the stronger the repulsion would be and the stronger the magnet would be. Okay, so as you can see in this middle zone here is kind of this like no man's zone of just repulsive, the repulsive barrier. That's what pushes magnets apart when you put them together and they're the same pole. Okay. Now for magnets with different poles, like here, the field lines, the magnetic field lines, just go from one pole to another like this. Okay, so even if we just draw the south pole going like that, the field lines are all going in the same direction, so they're not repelling each other. In actuality, they're drawing each other closer to each other. Okay. That's how the magnetic field lines would go in between two poles which are different. Okay. All right. Now, where do these magnetic fields come from? One thing we discovered while working with magnets and electricity is that if you have a moving charge, so for example an electric current, it can actually generate magnetic fields. So any electric current will have a magnetic field around it. Okay, now this is great for, I guess, if you were to create a magnet using electricity, because you just run a current and it'll create a magnetic field. Right, so any amount of electric current will create a magnetic field. Now, what about for most objects? Well, most objects do have electrons that move. So electron movement, every electron that moves will create a magnetic field. Now, the problem is with most objects is that the electrons don't move in any appreciable patterns. They have very random movements. So here's like here. None of the electrons, if each blue dot represents an electron, none of the electrons are moving in a way that would facilitate each of their magnetic fields kind of, I guess, moving in the same direction. Some of the magnetic fields will end up opposing other magnetic fields. They'll be absorbed or repel or anything like that. Or basically, this object doesn't have, any pattern to the magnetic fields that get created. So then how are magnets created? Well, some objects actually have non-random movement of electrons. So there are a few objects, mostly the magnetic elements, where their electrons have a tendency to move in the same direction. As such, they create a magnetic field that, rather than kind of canceling each other out, they actually end up reinforcing each other, because all their magnetic field lines kind of go in the same direction. Okay, so if this moving bunch of electrons will create a magnetic field, and the magnetic field will all be going in the same direction. And then if that happens, then you will have a magnet. If enough electrons are moving in the same direction, you can create a magnet. Okay. Now, the elements that do this, there's actually very few of them. The most common is iron, nickel, cobalt, gadolinium, and neodymium. Okay, if you're not familiar, these make really, really strong magnets. Really strong magnets for their size. Okay, so neodymium magnets, they're small little round disc magnets, and they're really fun to play with. Just don't swallow them. Iron, nickel, and cobalt magnets are more common, but they're not as powerful as the neodymium magnets, at least not commercially. Okay, now the reason they do this is because most elements, these would be our magnetic fields. So magnetic fields of groups of electrons. Okay, and notice that they all kind of, there's no pattern to them. They're all kind of going all over the place. So this, like here, this magnetic field would be canceled out by this magnetic, or these two magnetic fields kind of oppose each other, so they're going to cancel out. Same thing with this one and this one, and so on. So a lot of the magnetic fields in these groups end up canceling out other magnetic fields from other groups. Okay. Now with these magnetic elements, they're groups of electrons. So these groups of electrons, or the magnetic field of groups of electrons, more of them go in the same direction. So notice here you have a lot of magnetic fields going towards the right. So the majority, so this would be effectively a magnetized piece of metal or piece of something, and since all the magnetic fields are going in the same direction, at least a good majority of them are going in the same direction, it'll have a magnetic field that basically goes like this, because the majority of the magnetic fields are going in this left to right direction. So this material could easily be a magnet. Okay. It actually turns out that one of the easiest ways to create a magnet is to simply run a high current through any of these metals. The high current will force the electrons to all move in the same direction, and then you remove the current, and then you get a magnet. Right? It's how we can remagnetize bar magnets at school. We have one of these devices at school, so maybe I'll show it to you guys at some point in this unit. Okay. All right. Now, the direction of the magnetic field can be determined using a technique called the right-hand rule. The right-hand rule is used in a lot of things around magnetism and electricity and force and things like that. Okay, but there's a few different versions of it depending on the context of your problem. So if you'll have to be mindful of what the problem is asking and apply the correct version of the right-hand rule to that problem. Okay. All right, so the right-hand rule is used to determine the direction of the magnetic field, and this is based on the direction of the current. Okay, and through experimentation, we have come to the realization that the field, so if the current is going in this direction, so here's the current, okay, the right-hand rule says, okay, we'll point our, current in wire, okay, then we'll point our thumb in the direction of that current. Point thumb in direction of current. Direction of current. Okay. And then the way your fingers curl around it, so if you're using your right hand, if your current's going this way, your fingers should curl around it like this. Sort of like that. Okay. Let me redraw this. Alright, so if my current is going this way, then if I'm using my right hand, my fingers should curl around it like this. Okay. I highly encourage you to actually take out your right hand and try this. So point your thumb in the direction of the current and then curl your fingers around an imaginary wire, I guess. Okay, now curl the fingers, around the wire. Okay, and then the curl of your fingers, determines the magnetic field, determines the direction of magnetic field. There you go. All right, so in this case, the magnetic field is going in this sort of counterclockwise motion. Yes, counterclockwise motion. Okay. Now, generally, this is a little difficult to understand. So what we do is we have two different symbols. Okay, and so if I get this right, I always mess this up. Okay, so we have two different symbols. This one's a dot, a circle with a dot, and then on the other side is a circle with an X. There we go. Now, what do those dots and X's mean? Well, the dots mean that this is the coming out of page. And the X's mean going into the page. Okay, so the magnetic field goes this way, basically. Similar, so it goes out the page and goes back into the page. Out the page, into the page. Out the page, into the page. That. Okay, so that's the direction of the magnetic field. Okay, that seems kind of weird because in this current carrying wire, there's really no true north or south pole, but you can pretend it kind of is. Because remember, our direction of our magnetic field is determined by how a north pole would move. So if I put a north pole here, it's going to be pushed along this magnetic field going around like that. So you can pretend that this upper portion here would be a south end. So a south end would be on this side because the north pole is moving towards it. And then down here would be a north end, because the North Pole is being pushed around it. That's one way you can sort of look at it. Although I guess depending on what your position, you could actually make the same argument that the top here could be a north end, because if I have a North Pole here, it'll get pushed away from it and pushed towards here. So it really just really depends on what else is going on, because this particular wire, the way that everything is moving, it's kinda, you can basically make an argument for north or south on either end. But regardless, the right-hand rule will tell you what direction the magnetic field is going in, but not necessarily what the poles are, just a direction. Okay, just a direction. Okay, so this is for determine direction of magnetic field based on the direction of current, and this should be in a single wire. In a single wire. Okay, so this version of the right-hand rule works great if you're using a single wire. Okay. Now, if you're using a coil of wires is what we call a solenoid. Okay, so a solenoid is just a bunch of wires all coiled together. So if I were to draw a picture of a solenoid, it would look like this. Coil of wires, like this. Coil of wires. Yeah, so that's a solenoid. Coil of wires. Now this has you can use the right hand, oh, I have a picture of a solenoid, there's a solenoid. So you can use the right-hand rule to also determine where the magnetic field will go for this particular situation, but it just ends up being used in a slightly different manner. So like I mentioned, the right-hand rule is specific to, or has different versions for different problems. Here, let's suppose our current is going this way. We'll put a current going this way. There's my current. Okay, I guess the current goes around like that. Kind of hard to see, but I'll draw it in. There's my current is curling around like this. Okay, so the right-hand rule for this one is slightly different. Okay, so in the previous slide, last view. So in the previous slide, the right-hand rule was we pointed the thumb in the direction of the current, and then the curl of the fingers determines the direction. Okay. In a solenoid, the curl, you can represent the curl with your fingers. So curl of fingers is the direction of the current. The direction of current. Okay, so if you take your right hand and curl your fingers like they are, curl your fingers according to this picture here in the direction of the current. So if you take your right hand, your fingers should curl towards you. Okay, so if the fingers are curling towards you based on this diagram, then direction of the thumb is the direction of the magnetic field. So direction of thumb is direction of B. Okay, so if I'm not mistaken, if I use my right hand here and my fingers are curling towards me and down like I have here, the magnetic field, my thumb will end up pointing in this direction. That would be the direction of my magnetic field, is towards the right. Towards the right. Okay. So the right-hand rule is slightly different for solenoids, but not entirely different. But yeah, this thing just gets swapped. Okay, so be mindful of what your problem is, whether you're using a coil of wires. So this is the right-hand rule for a coil of wires, or if you're using a single wire. So the right-hand rule for a single wire is slightly different. Okay, all right. Okay, now. How do you determine the strength of the magnetic field? For a naturally occurring magnet that's entirely experimental, at least in my experience, it's always been very experimental for determining the magnetic field of a naturally occurring magnet. But for a magnet created from an electric current, that we can calculate. Okay, so if you have a solenoid, and most electromagnets are built using solenoids, the equation for the solenoid magnetic field strength is given as follows. Okay, so this is the magnetic field strength. So magnetic field strength is this magnetic field strength. Okay, I is the current, and this N here is number of loops per meter. Okay, and mu zero, this is the permeability of free space, which is sometimes called the magnetic constant. So it's very similar to Coulomb's constant as a way of making this equation work, or the universal gravitational constant also as a way of making this work. But the interesting thing is mu zero can be changed. So this can be changed depending on what's inside the solenoid. It can be changed based on what's inside the solenoid, based on core of solenoid. Because not all solenoids are wrapped in empty space. Sometimes they're wrapped around something, and depending on what that thing is, you can actually change the permeability and alter the magnetic field strength of your solenoid. Okay. All right. Okay. I think it's just number of loops. Well, we'll go through some examples and work this out. Okay. All right. So, current coils per meter. All right. So let's go through one example, and then I'll turn you guys loose on your assignment. Oh wait, after this. So for a charged particle, okay. For a charged particle, you can calculate the amount of magnetic force. So this is the amount of force that a charged particle feels inside a magnetic field. Okay. Basically, it means that more speed, because this is what V is. V is speed. So speed of charged particle. Okay, much like we did in the previous unit, this is charge of particle. There we go. Okay, and then B is magnetic field strength. Okay, so the magnetic field will actually exert a force on nearby charged particles. And the faster the particles are moving, or the larger the charge, or the larger the magnetic field, will create more magnetic force. Okay. Alright, so here's an example. That's what I wanted to do. So we have a solenoid, 25 centimeters long. It has 500 loops. If the diameter of the solenoid is 4 centimeters and has a current of 9 amps flowing through it, what is the magnetic field inside? Okay. Okay. So let's grab this. There we go. So a solenoid, 25 centimeters long. Or diameter. There we go. All right. So according to our equation, pen. There you go. So according to our equation, magnetic field strength. So mu zero times I times n, where n is equal to number of loops per meter. So this is going to be 500 loops per 25 centimeters, or 0.25 meters. This will be, I think, 2,000 loops per meter. All right, there we go. Okay, diameter of the solenoid doesn't actually matter, because it's just, yeah, that doesn't actually matter. Kind of a extra information, right? So we have a current 9 amps flowing through it. I'm going to calculate our magnetic, oops, I put an I in there because I know how much current's flowing through it. 9 amps. We have 2,000 loops. And I guess I should look up what is mu zero. Let's do a quick look. Okay, so in table of constants on the back of your textbook, mu0 has a value of 4 pi times 10 to the negative 7. So it's quite small. And this will have units of Tesla meters per amp. And like with every other constant, the units are there so that everything cancels out and you're left with a unit that makes sense. Alright, so let's calculate this out. So B will then be 4 pi times 10 to the negative 7 times 9 times 2000. And this will end up equaling, let's see, let's get my calculator. Alright, so let's multiply 4 times 9 times 2. I'll do my exponents later. So this will be 72 pi. 72 pi times 10. So we got 1, 2, 3 times 10 to the negative 4. And if you wanted to get an approximate answer, we just multiply that out. So 72 times pi, 226.19, 226, so 226 times 10 to the negative 4. In proper scientific notation, move it to there. So this will be 2.26 times 10 to the negative 2. And this will be in units of Tesla. There we go. Alright. There. So that's how I can calculate the magnetic field inside a solenoid. Okay. Solenoids are much more useful when creating magnets, simply because you can control how much magnetic field the solenoid creates. Permanent magnets and magnets you'd find in nature, they're a little harder to control or a little harder to create in the way that you want. They're also, you can also never turn them off. They're always on. The advantage of the electrically generated magnet is you can turn them off. Okay. Anyways, just the one example today. If you guys have any questions, you can ask me. You can ask me tomorrow, I guess, or whenever you see me next, or just contact me. You guys know how to contact me. I'm very easy to get in touch with. There's your assignment. And yeah, if you guys have any questions, you know where to find me.